Hello everybody, welcome back to another drill classic. This video is intended to serve as complementary material that shall give you an intermediate level understanding of bone anatomy and physiology. I will prepare you for hearing more intricate stuff by defining some commonly used terms and concepts in osteology, knowledge of which serves as somewhat of a requisite if one wishes to fully comprehend the evaluation of bone smashing series, as well as some future content I plan on creating. I guess you could skip this video and then Google something when you don't understand it, but I highly encourage you to stick around. We will firstly categorize bones in different subtypes based on their general anatomic architecture, then discuss macro and microstructure of bone tissue, define two-layer structures or the periosteum and the endosteum, examine types of ossification processes, as well as conduct a breakdown of bone matrix and explore what distinct role each type of bone cell serves. All bones in the human body can be classified by their shape and structure into one of the following categories: long, flat, sutural, irregular, short and sesamoid bones. I will briefly explain flat and long ones because the rest holds little importance for our interests. Firstly, long bones are characterized by their rod-like shape. They are hollow inside and filled with bone marrow. They are distinct in that they can be split into diaphyses, the hollow shaft composed mostly of dense cortical bone, metaphyses and epiphyses, which are largely spongy bone surrounded by thin cortical shell. In terms of looksmaxing, they will be interesting in the discussion of height growth protocols, as the femur and tibia determine your height. But this video topic is bone smashing, thus we will be much more interested in flat bones, as flat bones consist the majority of your craniofacial skeleton, as well as the scapula, sternum and ribs. Importantly, they do not contain the diaphyses, metaphyses and epiphyses. Instead, they are of a sandwich-like build with a layer of spongy bone in between two layers of compact bone. You might ask yourself, what is compact or spongy bone? Regarding how mineral deposits are structured, bones are divided into those two. Due to these structural differences, they will differ in aspects of density or porosity, three-dimensional structure, and metabolic activity. Thus, they have somewhat separate roles in the human body. Firstly, compact or cortical bone is a well-organized structure composing of circumferential lamellae surrounding osteons. Osteons consist of between 4 and 20 concentric lamellar sheets of bone with a defined boundary between one osteon and the next, called a cement line, a thin layer of organic matrix. Generally in biology, a lamella refers to a thin layer, a membrane or a plate of tissue, and these concentric lamellae surround the Haversian canal through which blood and nervous supply runs. Adult skeleton consists of 80% cortical bone by weight, and due to the low porosity of about 5–10%, cortical bone provides maximum resistance to torsion and bending and gives bone its compressive strength. Cancellous or spongy bone also contains lamellar bone, albeit with a different structure than the osteon. Cancellous lamellae are arranged in at least one, on a first glance, randomly formed trabeculae. In actuality, these trabeculae are built in such a way to absorb most commonly occurring forces in the optimal manner. Trabeculae do not contain Haversian canals, and instead their blood supply runs around the trabeculae. With a greater porosity of 50–90%, spongy bone makes up only 20% of the adult human skeleton and has significantly greater surface area per volume unit. It also possesses a high rate of metabolic activity and remodeling. Because the primary bone cells lie on the surface and are in a closer proximity to circulating growth factors and cytokines, it responds more rapidly to mechanical stimuli and regulation of calcium homeostasis. The primary function of cancellous bone is allowance of deformation and absorption of loads. In terms of microscopic level structural distinction, why is this lamellar structure even used? Can't your body just stack up some bone in a solid structure and call it a day? Well, your body always aims to shape the bone in such a way that it resists and absorbs forces most efficiently. Because bone tissue isn't free, it costs your body both resources and to build and maintain, Plus it's heavy, so you expend more energy the more bone mass you have to move around. That's the reason why birds have quite weak and hollow bones compared to mammals. Due to complicated biomechanical reasons, the type of structure that offers the optimal amount of strength for an amount of bone is exactly this lamellar structure. The pattern lamellae are shaped and positioned in allows it to absorb and distribute loads very efficiently. There are 4 general forms of lamellar bone: osteon, trabecular, circumferential, and interstitial. On the other hand, woven bone forms the embryonic skeleton after birth and slowly gets replaced by lamellar throughout development. That is why babies have more flexible bones. Another instance is when your body needs to create a quick bone formation and doesn't have time to organize it into lamellar structure. Woven bone is made, and you can sort of think of it as a SOS mechanism. When your body is in dire need of building new or repairing old bone, it builds an archaic bone structure or woven bone. After its formation, your body will start the process of organizing that anarchic structure into normal lamellar bone, which means that in any moment you don't have much woven bone inside you. It mostly occurs when you break something or maybe bone smash. Another 2 terms you might have seen are periosteum and endosteum. Basically, the periosteum is an outer layer that covers all parts of bone except of enclosed joint capsules. Its functions are to isolate bone from surrounding tissues, but it is also a primary participant in bone modeling drifts, thus it is involved in bone growth and repair. That is because its surface is covered by osteoblasts to a degree, but also osteoprogenitor or stem cells that can differentiate into osteoblasts and enact bone formation that way. However, active osteoblasts make up only 5% of bone surface in the adult human. 94% of it is covered by bone lining cells and the other 1% by osteoclasts. The endosteum is a layer that lines the marrow cavity, trabecula of spongy bone, and central canals of inside osteons. Similarly to the periosteum, it contains osteoblasts, osteoprogenitor cells, and osteoclasts, thus it is very active in bone growth and repair. Now that we know some basic terminology when it comes to bone structure, we can start getting closer to what we are interested in with bone smashing. Thus, I want to touch upon types of bone formation. In terms of embryonic development, one is largely of mesodermic descent. Bone forms in one of 2 ways: endochondral ossification and intramembranous ossification. The hallmark of endochondral ossification is bone formation through a cartilaginous intermediate. It is the predominant process involved in long bone formation. This is the basis of longitudinal growth of long bones at the physial plate. Endochondral ossification is initiated by the proliferation of chondrocytes into hyaline cartilage framework with 4 distinct zones. The resting zone is furthest from the site of bone formation and contains normal chondrocytes. As the chondrocytes proliferate in the proliferation zone, they hypertrophy and release alkaline phosphatase, which eventually results in chondrocyte apoptosis and the release of angiogenic factors, including vascular endothelial growth factor. The zone of dead chondrocytes, or the calcification zone, creates a barren matrix that promotes capillary ingrowth and migration of osteoprogenitor cells. The osteoprogenitor cells then differentiate into osteoblasts and produce bone. This will be interesting in the future because yet again it relates to height growth protocols. Flat bones of the face and clavicles are predominantly created through a biological process called intramembranous ossification. In contradiction to endochondral ossification, the hallmark of intramembranous ossification is spontaneous bone formation without a cartilaginous intermediate. Intramembranous ossification occurs with the spontaneous development of an ossification center within an extracellular matrix by differentiation of mesenchymal stem cells into osteoprogenitor cells, then proliferate and differentiate further into osteoblasts. To put it in simpler format, it is a process in which your bone quote-unquote invades neighboring tissue, typically the dermis, and ossified by depositing mineral and collagen structures. That type of ossification is responsible for distraction osteogenesis, and theoretically it would be also responsible for the adaptive response that arises from bone smashing or mewing, if there is one. Thus, it is presumably a key physiologic phenomenon for looksmaxing. This presents a question of what is the composition of bone after these formation processes. So let's briefly analyze that. 90% of bone is the matrix, while only 10% are alive and metabolically active cells. Of the matrix, 2/3 are made of minerals, hydroxyapatite to be precise, and it serves a role of creating structural integrity and strength, but also as the body's reserve for minerals like calcium, phosphorus, and magnesium. Other third is collagen tissue, primarily type 1 collagen, and it provides elasticity and bending strength. Although bone consists of just 10% actual cell tissue, it will be false to assume it is an inert dead tissue that just provides our body structural support. That is because mineral and collagen structures are constantly going through a process of degrading and constructing back themselves via modeling and remodeling. That job is done by various types of bone cells, and its intricacies are discussed here. These bone cells consist only 10% of bone but are highly metabolically active cells. So let's begin by differentiating between 4 main types of bone cells and describe their distinct physiologic roles. As I mentioned when I talked about the periosteum, osteoblasts line the surface of bone, and in normal conditions the coverage is around 5%. Their role is that of bone forming cells due to the ability to synthesize and secrete organic bone matrix. Osteoblastic activity is marked by alkaline phosphatase release, and primary mediators of osteoblast differentiation and activation include bone morphogenic proteins and other members of the TGF signaling family. After the activation, they have 3 fates: remain quiescent osteoblasts lining bone, become osteocytes, or return to their original form as osteoprogenitor cells. Now notably, even if all osteoblasts lining bone surfaces activated, they don't possess much bone formation power. Due to that, there exist osteoprogenitor cells that act as stem cells. Osteoprogenitor cells remain dormant and undifferentiated until receiving signals to migrate to a site, proliferate, and differentiate into osteoblasts. They reside in the bone canals, endosteum, periosteum, and marrow. Osteoclasts are multinucleated cells whose role is that of bone resorptive cells. They attach to bone and solubilize it via acidification, allowing matrix phagocytosis. There are various factors and cytokines that regulate osteoclast formation and activity. These include some inflammation-related signaling pathways like NF-kappa B and interleukins 1 and 6, but also calcium homeostasis regulators like PTH, vitamin D, calcitonin, and osteoprotegerone. Most of the mentioned signals originate from various processes that are happening in the body that might or might not be directly related to bone, but there is another sort of signal very relevant to us, that is of mechanical origin. It occurs as an adaptive response to physical conditions that your body finds itself in. Obviously, this type of signal is very relevant for bone smashing and thus will be discussed to a greater extent in future videos. Cells that detect mechanical stimulation are osteocytes, and they account for 90% of all bone cells. They are osteoblasts that have surrounded themselves with organic matrix to live within vacuoles called lacunae. Once surrounded by matrix, they develop cytoplastic projections that transfers the bone and allow direct communication with other bone cells. Osteocytes' role is still not eluded to a full extent, but it seems like they are involved in a lot of processes besides the adaptive response, like regulating remodeling and mediation of calcium homeostasis. They can also be promoted to directly resorb bone by parathyroid hormone and might be involved in hunger signaling. This pretty much sums up everything you need to know about bone anatomy and histology, so you can fully understand the ensuing content. There is but one anatomic concept I left out, which is the BMU. Due to the sheer complexity needed to execute bone remodeling without compromising bone integrity, human body ingeniously regulates the process via organized cell units called basic multicellular unit. I have left it out because including it would require me to explain details of bone remodeling and the difference between modeling and remodeling, as well as how they relate to the previously mentioned formation and resorption activities, aka that which serve to adapt bone to physical circumstances, regulate calcium homeostasis, and resorption as a byproduct of inflammation. This is all done in the episode on bone modeling and remodeling, and as I said, this one exists to help you better understand all other content. So please like, share, and comment for the algorithm, and subscribe so you don't miss out any of the future content. And goodbye.